Hello everyone. So in the last lectures we discussed about phase transformation due to shock wave propagation. So in today we will start a new topic. So this is experimental techniques to produce dynamic deformation. We have already discussed a few techniques earlier like split Hopkins and pressure bar. So now we will discuss little details about these techniques. So we have even discussed about different strain rates. So here in this slide is increasing order of strain rate. I will write epsilon dot for strain rate. So if you see here at a very slow low strain rate, so 10 to the power minus 7 or minus 8. So we have like we can consider about creep and stress relaxation. This is basically we call creep like viscoplastic materials response. What is this right response here? And then we know that the quasi-static deformation, which is we can actually differentiate from quasi-static and dynamic. So the strain rate is probably 5. This is second inverse. As you know, the strain rate unit is second inverse, reciprocal of second. So if it is less than 5 per second, and then we are classifying it as quasi-static, and then if it is higher than that, we are saying that dynamic. So there are different subdivisions of dynamic. So for quasi-static test, we know that hydraulic, servo hydraulic or screw driven testing machines, we know these universal testing machines so can be found. And so this, as you know, that the quasi-statics we have static equilibrium. So in these machines or test with constant cross head velocity. So and we assume that the stress is same throughout the length of the specimen. Stress same throughout the length of the specimen. However, in today's lecture we will be more focused on the dynamic part, not these quasi-statics. So we will talk about higher strain rates, higher than let's say 5 per second. So as you can understand from here that the higher than 5 per second is these strain rate range, the inertial forces, force of inertia, or we like inertial forces, are important. These are important, or effect of inertial forces is significant, and below that strain rate inertial forces are negligible. Forces negligible. So when you increase the strain rate, more and more inertial effects will be there. So in the dynamic low means probably we can say that below 1000 10 cube. So below 10 cube probably we can call that dynamic low. So that includes high velocity hydraulic or pneumatic machines, and another one is cam plastometer. So here, as we know, we will get wave propagation. So in this range, for the inertial force are important, this range. So as you know that we will get wave propagation, not in the static case. In quasi-static case we do not get wave propagation, we get static equilibrium. So here we have wave propagation in this case. So in these cases the mechanical resonance in the specimen and machine is also important. So, when you go a little higher in this table, so let us say we have dynamic high range where we have Taylor and Will test, Hopkinson bar, which is very widely used, as we already have discussed several times, as HPV, right, split Hopkinson pressure bar, and another one is expanding ring test. So, the boundary is probably somewhere, you know, around in the order of 10,000 to hundreds of thousand. So, this is dynamic high, and even there are higher strain rate tests. So, which includes the explosions, explosive tests, and then normal plate impact, then inclined plate impact that can produce pressure and shear, then exploding foil, and then pulse laser. So, you can see that strain rate can go up to 10 to the power 7, so high. And if we talk about nuclear detonation, that is even higher. So, if we talk about nuclear detonation, that can be even 10 to the power 9 per second or even higher. So, higher. So, at so high strain rate, how the material will behave, it will be very difficult to predict. Even I think at a strain rate of 10 to the 6 or 7, also it is very difficult for our scientists and engineers to know about the mechanical behavior of the material. So, in this case, if it is dynamic low, also we will have elastic wave propagation, elastic wave. Then if we have higher amplitude, we can see plastic wave in some of these tests, plastic wave propagation, and then the plastic shear wave is you can see from inclined plate impact, shear wave propagation, and then at very high strain rate shock wave propagates. So, this is now the entire picture is quite clear to us. This is the table from the Mark Mayer's book. So, we have the boundary 5 per second, and we are differentiating that this is dynamic on the top of that strain rate and quasi-static on the bottom, quasi-static. So, where we have static equilibrium and stress same throughout the specimen. So, now we will discuss few of these tests, few of the commonly used tests, and also we will go through how we measure the strain rate. So, in the very beginning, in the initial lectures, we discussed about the calculation of the strain rate. We will again repeat these discussions. So, to calculate strain rate, which we will represent by epsilon dot. So, here you can see a tensile specimen, you have we are using a UTM machine at high speed. So, the velocity at which we are extending it is V naught, and let us say our V naught is I would write it here. So, V naught is equal to 1 meter per second, and then the length we measure from here to here, that length L naught. So, L naught here is let us assume that 0.1 meter, or let us say 100 millimeter. Now, the final shape is something like this. Final shape is something like this, and the change in this length, let us say, is delta L. So now we need to calculate the epsilon dot. Epsilon dot is the strain rate is, we use strain rate by the way, not velocity of deformation. We do not use the velocity of deformation here in this case V naught. So we do not use that, we use the term strain rate. And what is strain rate? Strain rate is it's the rate of change of strain with respect to time. So its unit is second inverse. So now strain d epsilon, we know that if we take it at time t equal to t2, so the strain is epsilon 2, and then time t equal to t1, let us say strain is equal to epsilon 1. So here in this case strain is equal to 0 at time t1, or let us say this is corresponding to t equal to 0, and here let us say t equal to t, this corresponds to this, this corresponds to this, and this will give us that epsilon 2, which is delta L by L naught. Okay. So now d epsilon is actually delta L by L naught, and what is dt? We are taking as V naught by delta L. So this is your velocity of the deformation V naught divided by the change in length. So that will give us the time required to change the length of the specimen. So that is nothing but V naught by delta L. So V naught by delta L, it will look like this. Oh, sorry, here, sorry. So we so now what is dt? The time required for the specimen to have these delta L change in length will be equal to delta L by V naught. V naught is this velocity of the formation. So now this dt expression we will put it here. So that will give us, as you can understand, this delta L will cancel out, that will give us V naught by L naught, and that means from here V naught equal to 1, L naught equal to 0.1, that will give us 1 divided by 0.1, and as you know V naught which have meter per second, 0.1 is meter, so that will give us 10 per second. So our strain rate in this case for this tensile test is 10 per second. So that is the strain rate, but there can be some other examples where the calculation of strain rate can be little different. We need to show you that calculations, how we do that. So this is the case, that's a high velocity projectile. This is a projectile hits the rigid target. This is the rigid target, let us say rigid wall, and it has a velocity v, and let us assume its initial length of the projectile is L naught, and the final length means after hitting the rigid target, it will take a conical shape, and the change in length, suppose I am drawing the undeformed projectile close to this is the undeformed projectile length I am drawing here. So and this is the final shape, deformed shape. So this delta L is the change in length of the projectile. So let us assume that to calculate the strain rate, let us assume that the velocity is very high. Let us say the projectile is moving at 1000 meter per second, and L naught, the initial length of the projectile, let us assume it is 5 centimeter, or let's say 0.05 meter, and then delta L is, let's assume, half of it, 0.025 meter, or we can call the 2.5 centimeter. This is 5 centimeter. So what we can do is to get the strain rate out. So this will be like delta L by L naught divided by time, the time taken to have delta L deformation. So that will be equal to delta L by L, which will be equal to 0.05 divided by T. Now we assume that linear deacceleration is happening. The projectile linearly deaccelerate. Okay. So that means, let's say we have time versus velocity. So velocity is v naught, and after time t, this, let's say time t, so velocity will be 0. Here velocity will be v naught, and this area will give us the distance traveled. From the basic kinematic equation, we have v initial plus v final multiplied by t. So in this case, we have the initial velocity is v, which is let's say 1000 meter per second for our case, and the final velocity is 0. We have t here, and then in this case also the initial velocity, probably if we are writing this can be v, actually that is not v naught, so this will be v, and that will give us the time. Now how to get the time? Time is equal to twice s divided by v. So v is 1000 meter per second, and twice s. S is nothing but the 2 multiplied by 2.5 centimeter. That means the reduction of the length. That means these projectile move to this position, so that is equal to s. We can probably keep the time value here, and then what we can do is we can go to the epsilon dot, the strain formula, and here what we will get is epsilon dot is equal to 0.025 divided by 0.05. Here now we will put the time 0.025 multiplied by 1000. So this will cancel out, and that will give us 10 to the power 4 per second. So our strain rate in this case is 10 to the power 4 per second. So this is the second example we did for strain rate calculations. So we can do one more. So this is this involves shock waves. So this is the third one. I will write the third example to calculate the strain rate. So in this plot, if you can see, we have, let's assume that the shock wave, we have the sigma stress amplitude, and that is in gigapascal, and in the x axis we are showing x, and at this point it is at a very high pressure, 30 gigapascal, and as you know, this is the shock front, the steep shock front, and here what is happening here is this is the material before shock wave passes through, and after that the shock wave passes through, the material is here. So the width, if we draw a line here, the width of the shock front, the width of the shock front is this one, that will be very thin. That width of the shock front will be, let's assume it is as 5 micrometer. So it's a very thin shock front. So this is the width of the pressure rise. Plastic deformation happens during the rise of shock wave, and as you know that the width of that rise zone is very small, we can assume it to be 5 micrometer, and this rise time of the shock wave and the reduction of volume will determine the strain rate. So if you want to know the strain rate, so that rise time, the time required to for the pressure rise from here to here, so the pressure rise time, and also the time also the volume reduction or volumetric strain will give us the strain rate, or otherwise we can draw it like this. So these two will give us the strain rate. Now you will see from our table 4.1 in our Mark Mayer's book, you can see that for, let's say, this material is copper, the material is copper, and for copper 30 gigapascal, from the table 4.1 what you can get is, you can get the shock wave parameters like pressure, density, volume, specific volume, and then shock wave velocity, particle velocity, and the sound velocity. So now what we need here is, we need the shock wave velocity and V by V naught, the specific volume. So from there, corresponding to 30 gigapascal and material copper, so we will get the value. So this value from the table says that it is 4.95 kilometer per second, and V by V naught is 0.863, the specific volume. And we know that shock front width is 5 micrometer, which we assume to be that will be very small value. So that is, we assume that S equal to 5 into 10 to the power minus 6 meter, and then epsilon, the strain, is like 1 minus V by V naught, which will be equal to 1 minus L by L naught. So because assuming area is constant, so what we will get is 1 minus, we have the V by V naught value here, 0.863, so that will give us the strain is 0.137, and then what we need to do is, we need to get the time, that is the rise time, where we have that rise time t. Okay, this time will be s, the distance of the width. So you can see the time required to raise the pressure. So that is the s, which is 5 micrometer divided by the shock wave velocity. So that will give us 5 10 to the power minus 6 divided by shock wave velocity is this one. So that is 4.95 into 10 cube meter per second. So that's give us, it is 10 to the power minus 9 second. So that is a very small value. So t equal to 1 nanosecond, and then we can now calculate the final strain rate, so which will be equal to epsilon by t.
So this will give us 1.137 divided by 10 to the power minus 9, which will give us 1.4 10 to the power 8 per second. So see, this is a very high strain rate. If you want to go back to our earlier table, so you can see that 10 to the power 8, as we told, that at a very high strain rate the shock wave can form. So we are discussing about the experimental techniques for dynamic deformation. The history goes back to 1905. In 1905, Bertram Hopkinson first tried dynamic experiment on material, and came to the conclusion that what the conclusion is, the dynamic strength of the materials at least twice of their strength at low strain rate, at least twice of the strength at low strain rate. So that's what he found out in around 1905 AD. Unfortunately, he died in the World War I. He was working as a pilot, and also it was known to people that the steel undergoes ductile to brittle transition. At high strain rate. Some of you already asked that questions to me, that what I told you in the initial class, that if we increase the strain rate, then tensile ductility increases. But yes, it's not for all materials. Sometimes the material look like more brittle or less ductility at higher strain rate. So these are some information even known long ago, but it depends on different material. So it is very material specific, and so we will we need to know this response of different materials. So different materials behave very differently. Also the strain rate dependence of flow stress which we already discussed, that is we call strain rate sensitivity. In the initial lectures we discussed that sensitivity. This should be incorporated, this strain rate sensitivity should be incorporated in computational calculations, computational codes. So for example, very commonly used plasticity model, what people use for high strain rate calculations is Johnson-Cook equation, or we would better call Johnson-Cook plasticity model. That will see how the constitutive behavior looks like is sigma effective sigma naught plus B epsilon effective to the power n, thus it's not ended here. So this is 1 plus C natural logarithm of strain rate 1 minus T star to the power m. So here sigma naught B C N and M are material parameters. That means they are specific to materials. So different materials have different material parameters. So these parameters allow us to get the a relationship, that is the constitutive relation, that means the stress dependence on strain rate and temperature. So what you can see here in this plasticity model or Johnson-Cook model, it has all strain rate and temperature terms, and sigma effective and epsilon effective are the effective or equivalent values, and T stars are actually normalized temperature. That's why we have used superscript star. Temperature. Important to note that, so these parameters cannot be obtained from first principles. So we cannot calculate those without doing any experiment. So these are experimentally found out. Experimentally determined. So these parameters, they cannot be obtained from first principles. So that we should take care of that. So for different materials will behave differently. That we need to do some experiments. Let's say split Hopkinson pressure, then we see the response of the material, how it deforms at different strain rates. So from that we can get these material parameters out, and then we can do use those parameters into computational codes, and then get the correct, or we can approximate the predictions of the material behavior from the computational code. So now we will see some materials behavior here. Let's say if we talk about different materials. So in these two plots I will show you different material. These are stress strain curves, stress strain, let's say stress and strain. Here is also stress and strain. So this is stresses in this has it in KSI is the unit here. So KSI is the unit, and here strain, as you know, this is without any unit, but we have 10 to the power minus 2 here multiplied with all the scale. So now if we talk about the this first plot, so we have let's say 20, 40, 60, 80, 100, 120. So for aluminum 7075 material, aluminum, I will write that about the material, but let's see the plot. So it will look like something like this. So this is the material is aluminum alloy, and it is 7075 T6. T6 shows the heat treatment condition, but 7075 is the basic material nomenclature designation for this particular aluminum alloy. So it looks, the stress strain curves looks like this, But when you have a so this is at particular strain rate, let us say it is at strain rate 0.03 per second, epsilon dot is 0.03 per second, and if you increase the strain rate, let us say 4 per second, epsilon dot is let us say 18 per second, and then epsilon dot is 560 per second. So these are the experiment done by in the reference Maiden and Green. It's a very old experiment in 1966. So what they found is all the curves for all different strain rates, they found not much difference. There is no significant difference, and all the curves are very close to each other. So that means this material is strain rate sensitivity is not high, and it is almost negligible. But in the other case, this material is titanium 6%, aluminum 4% vanadium. So this alloy is, especially a titanium alloy, is very popular for suppose biomedical applications, and especially nowadays it is very popular in 3D printing, metal 3D printing. So they use this material. So now let us assume we are drawing a stress strain curve, for let us say a strain rate 0.004 per second. That is a very slow strain rate, quasi static range, and then let us say if we increase the strain rate little bit, it will show a different behavior. This is strain rate 0.08 per second. We have it is increased to let us say maybe 20 times, and then if we have higher strain rate like epsilon dot equal to 1.5 per second, and then even higher, it is 20 per second, then what will happen is this stress strain curve will be different. So this portion, the elastic portion, will look almost the same, and but if you go when after the yield, so it will be different. So that means it's a highly sensitive, this material is highly sensitive to strain rate variation, or simply I will write strain rate. So similarly, there are more materials we want to discuss. So let us say this is true stress, this is in megapascal, true strain. Similarly, here also the same, true strain and true stress, better to write it full, true stress and true strain here in megapascal. There are two material we wanted to show. The first one is pure titanium, commercially pure titanium alloy, and here is we have another alloy, this titanium metal, not an alloy, and here we want to show the another one is tantalum. So for pure titanium, which is the reference is both from Mayers and co-workers, so Mayers et al. 1994, and the other one is Chen et al. I think a co-worker of Mark Mears. So if you see in this case in tantalum, it's already the curves are drawn, and the strain rates I just wanted to tell you, this one has a strain rate of 8 into 10 to the power minus 4 per second, very low strain rate, quasi-static range. And then if you increase the strain rate 10 times, which will be also quite similar, there is a quasi-static range. And then if you increase it to a dynamic range, and actually a very high, it's a high strain rate range, not, we cannot say it's a very high strain rate, because these are all relative, these terms are. So if you talk, if you say that split Hopkinson press server has high strain rate, then what will happen to explosive test, or what will happen to even nuclear detonation? So in this case, then 3500 per second is a high strain rate. So you can see that this tantalum has shown the strain rate sensitivity. And in this case, for pure titanium, what we can get is this is the curve, because of the failure. So this curve is strain rate 0.001 per second, and then another curve is another curve we want to show you. This is has epsilon dot 3.9 per second. Then two more curves, 5500 strain rate, this will show some fluctuation, 5500, this has epsilon dot is 5500 per second, and then another one is even higher strain rate. So this has epsilon dot is 7700 per second. So these are it's very difficult to get a trend. Like if you can see that the quasi-static range you are getting more ductility, but in the if you compare the high strain rate case, you can see that if you increase the strain rate, you are getting more ductility. So which is kind of contradictory. So whatever we have shown earlier is we have shown in the earlier couple of slides, we are showing strain rate sensitivity. So we took different strain rate range in the earlier. We have shown different strain rate range. So 10 to the power minus 3 to 10 to the power 3 per second, whatever we shown in the earlier cases. But we should understand these materials are very different in structure. If you see especially the crystal structures, as you can understand, we have shown about aluminum alloy, but basic aluminum has an abscisic structure. Then we talked about titanium has a hexagonal closed packed crystal structure, and then tantalum Ta has a BCC structure. So the plastic deformation, as we will discuss in the later part also, it depends on the crystal structures that you have probably studied in your BTech material science course. So so different materials basically will behave differently. We need to get the material parameters out from the experiments. Let's say assume from split Hopkinson press server, and you now understood that those material parameters cannot be calculated from the first principles. And so this curve, what we want to show you in this slide is from a reference Clifton's group. Clifton, this is a reference from 1983. What this report says is, if you increase the strain rate at a very high strain rate value, so this is strain rate, by the way, sorry, this is shear strain rate, and in the y axis we have shear stress. that is in megapascal. So what happens here is, this is a material, this is aluminum, this is aluminum, we write it as aluminum 1100. So this is so this material, so what happened, there are three curves here associated with different plastic strains. Let us say the first curve, the first one corresponds to a plastic strain gamma, that is 0.05, and the second one is gamma equal to 0.1, and the third one is gamma equal to 0.15. So this says that the shear stress is very high. Shear stress is very high when it reaches a 10 to the power 5 strain rate. So that's quite interesting. So that means that the profound effect on the computational predictions of very high velocity projectiles or shaped charges and other high strain rate events. So so the hardening is very high, hardening increases to a very high value. We need to understand here the first thing is the plastic deformation mechanism, how the deformation process is happening. It changes, let us say it changes from fully isothermal to fully adiabatic. So we will discuss more about these in later chapters. So this can give us the shear instabilities or shear bend. So we will discuss this in the later chapters. So and also second thing is the constitutive models, that constitutive relations need to be modified to models like we have shown the Johnson-Cook model. Constitutive models are to be modified for this extraordinary or sorry for its unusual behavior at high strain rate range. That has a limiting strain rate. If you see that this has a limiting strain rate for the strength of the material becomes infinity. So at that 10 to the power 5, so strength becomes infinity. So we need to know that whether a limiting strain rate is available, and then how the plastic deformation mechanisms decide that limiting strain rate. What we discussed in today's lecture is that we discussed the basics of the experimental techniques, the range of different strain rates of the experimental techniques for to produce dynamic deformation. So we also discussed how to calculate the strain rates for different cases for let us say uniaxial tensile stress specimen, and or for the projectile impacting a rigid plate, or for a shock wave. So we have seen how the calculations can be done, and also we have seen that the material sensitivity, material strain rate sensitivity is different for different materials. We discussed about some of the very well known materials, and we have seen that the constitutive relations like Johnson-Cook plasticity models have some materials parameters, that can be determined from the experiments, for example Split-Hopkins and pressure bar experiment, and these parameters cannot be found out from these first principles. So we will continue these discussions in the next lecture. So we will discuss some of the commonly used experimental techniques. Thank you.